knowledge, facts, and examine. Our program today features an impressive lineup of speakers, each showcasing cutting-edge research and application in various fields. The main speaker is going to be talking on computational biology and then some other aspects of application of mathematics. We will delve into the latest advancements, challenges, and successes in applied mathematics. This workshop would not be possible without the support of the Vice Chancellor, the BBC, the Registrar in Essentials, and our HOD, Professor Lupa, the Dean of Mathematics, and all the lecturers. I extend my gratitude to each of them for their contributions. Throughout the day, we encourage lively discussion, networking, and idea exchange. We arrange some few specific activities, like we were able to also meet with our speaker, guest speaker from Morgan State University for collaboration, for networking, and all of that. As explore the intersection of mathematics and real world challenges, let us remember the power of interdisciplinary collaboration. Let us strive to translate mathematical insights into tangible solutions, driving positive impacts in the world. Further ado, I want to appreciate everyone that I saw, and I believe that by the time you are going to leave here, you will leave here with a mathematical experience that will never leave you forever. Thank you again for joining us. Let's make today a stimulating and productive experience. Thank you. Let's speak for people that will take that those short tutorials, powerful that have been said, visual collaboration, and everything that I want to have. So people, before we go on, I'll also recognize the person, another lecturer from the department, senior lecturer for that, who we also want to be IJW to sit to the professors here, the person of Dr. Iyiola Olaniyi. Yeah, many functions, let me know the IJW. All right. So we want to, on the occasion, bring up the Vice Chancellor, who is ably represented by the librarian, to speak to us. And I know that he has an important visit for us. And so please permit me again to bring Professor Isaac up for the Vice Chancellor's speech. Thank you. Let's do the club as we bring our listening representing the librarian. You are welcome, sir.
Distinguished members of the high table, starting from the director, Professor Emmanuel Bakari. Ladies and gentlemen, well, let me say that I don't prepare the speech. In fact, I was just maybe the venue of the matriculation. When I thought I was just coming as a friend to the director. Not where I'm going to be doing it. It's like somebody with a pastor, like Professor English. I'm not prepared. Pastors are not always prepared. So nothing is pastor impromptu. Therefore, I want to, on behalf of the Vice Chancellor, Professor Iyiola Olaniyi, welcome to this workshop.
You know, when we talk of lectures, seminar, things,
in one thing or the other. And for this reason, I want to urge us to be attentive, to be diligent, because no knowledge is lost. And I want to assure you that you collaboration and even gaining of skills like the director rightly observed, mathematical experience for that matter. Funny enough, when I was in the secondary school in those days, mathematics happens to be one of the subjects I dread. I have phobia for mathematics. But unfortunately, I ensured that I passed it. And so pass with it. Because thank you.
Sir, that you are running chair on for this workshop that is about to start. Thank you so much. We are grateful, sir. Now, we should be going to this speech, but you know that in the university today is also the matriculation day. But despite that, the day of the Faculty of Science is on its way, coming to join us from that occasion, which is ongoing in the other side of the university. So we'll soon have him when he comes. But then our head of department is here seated already. And one thing that I've seen, I've known about him, I have at least twice listened to 2 messages from him in many of some of our events. They are always loaded. And I'm sure that today is going to bring us also again. I'm always very attentive when such messages come up. So please, I want you to pay attention and pick a lot of things to learn from these messages. They are not just messages to while away the time. Please, I want you to join me to bring my own HOD, our HOD, the person of Professor Lukman Akiola, to bring us a message, the HOD speech. Thank you so much, sir.
The Vice Chancellor, ably represented by the University Librarian, Professor Isaac Busayo. And before I go on, let me use this opportunity to congratulate our librarian on his elevation to the rank of a full professor. So, congratulations. The director of ICAMDA, our own Professor Bakari. So I think I can officially say congratulate you. Your elevation to the rank of a full professor. It was approved by the University Council last week or 2 weeks ago. So congratulations. Our guest speaker of today, all the way from Morgan State University, Baltimore in the United States of America, a person of Professor, Iyiola. So you are welcome, Prof. So we appreciate your coming. So we know that we are going to learn a lot from you. So thank you very much for coming. I have my colleagues in the department, our senior professors, Professor Abolari is here. So thank you for joining us. Professor Adiefa, thank you for joining us. So we all know, so these are the pillars we have as far as mathematics department is concerned. So they've been assisting us a lot to make a meaningful impact in training the students, and I've been enjoying their cooperation a lot. So I think I appreciate your contribution. You are welcome. Thank you very much. My other colleagues in the department, other lecturers, so I welcome you all. And the member of staff of most departments that are here, apart from the lecturer, if there's any, I'm talking about the non-teaching staff. The member of staff of Canada, so I recognize you. All participants from within and outside the university. So ladies and gentlemen, it pleases me this morning to stand before you to give an opening remark to commence the real business of the day in this one-day seminar organized by the International Center for Applied Mathematical Modeling and Data Analysis, Uganda, in conjunction with the Department of Mathematics, Federal University Oye-Ekiti, Nigeria, on the topic Generalized Differential Equations, Numerical Solutions and Application in Biological Models. And this is to be delivered by Professor Olaniyi Iyiola, all the way from Morgan State University, Baltimore, Maryland, in the United States of America. So differential equations are one of the major branches of mathematics that deal with mathematical equations that describe how a quantity varies over time. Of course, we know that we have many types of differential equations that you are familiar with. So talking about differential equations, partial differential equations, linear differential equations, non-linear differential equations, stochastic differential equations, and many more. And we have different approaches of solving differential equations depending on the type of the equation under considerations. And one we are really familiar with at the basic level, looking at the change of variables. We are familiar with that method of undetermined coefficients, reduction of order, linear method, Laplace transform, variation of parameters, matrix methods, initial value problems, boundary value problems, and numerical methods. So we are familiar with many of these methods. Today, we are talking about generalized differential equation. When is the differential equation said to be generalized? I am not here to answer that question, since I'm not an expert in that area. So we are not talking about group theory. So when we are talking about differential equations, I know my limits. I don't want to pass my boundary. So I say plain like that. That is why we have Professor Iyiola in our list to shed more light on the topic. He will take us through how to use one of the identified methods of solving the differential equation, numerical methods, to solve these kinds of differential equation. As we all know, mathematics is a discipline that is born out of necessity. Right from the onset, the need for one form of mathematics or the other gave room to creation of such mathematics. So it's always an application-driven discipline. If you look at the development of number systems, after a series of contributions from many ancient societies, the ancient Mesopotamian, the ancient Egyptian, the ancient Greeks, the Hindus, the Arabs, and the people of Western Europe, they finally arrived at the decimal number. This one gave room for formation of number, natural number, and the integers. As time progressed, solutions to root of quadratic equation and other polynomial equations, it was discovered that the integers are not indeed enough. This also gave room for advanced set of numbers, like the real numbers and the complex numbers. So the trend has continued ever since today across all branches of mathematics, where the need for solving one mathematical problem or the other or solution be physical and biological sciences. And even in technology, it is relevant to add that sharing ideas on problems and solutions has always been through publications in books and academic journals, organization of conferences, symposium, workshop, seminars, and the likes. So that's the justification for what we are doing here today. In line with that, this is now the moment to learn about numerical solutions to generalized differential equations and how this will be applicable in biological models. We all know that mathematics has been a crucial role in biological sciences by enabling the creation of a quantitative method that describes and predicts biological phenomena, including population dynamics, disease spread, cell behavior, and evolutionary patterns. We have an expert in the house to do justice to the topic. So at this juncture, I want to digress a bit to appreciate the director of International Center for Applied Mathematical Model and Data Analysis, ITANDA, Professor Emmanuel Bakari, for making this possible. He has been doing us proud in the department and the university at large through various human developmental programs. He has been funded through the center. Just recently, he organized a 3 months fully sponsored internship program for 16 newly graduating students of our department, which they completed about 2 weeks ago. We invited this one to stay in the department. So I'm not the guest speaker. Our distinguished participants from far and near, I want to engage you to pay rapt attention as our lecturer of the day, Professor Iyiola, will be doing justice to the topic. So let me stop here and appreciate you for listening. Thank you very much.
Thank you so much, sir. Again, a very beautiful presentation at that. Thank you for a well-scripted message. Thank you. We are very grateful, sir. All right. I told you we are professors in the department, but before they bring their goodwill messages to us, I have the Dean of the Faculty of Science, who has just entered to the hall of events, the person of Professor Ajiboye. Please, I want us to bring him to the high table. Thank you so much. We are really happy to have you. The house is actually full. It's a full house. Thank you. All right, before the dean comes up with his speech, and we'll have a farewell message from our professors from the department. So you permit me, all right, while the pleasantry is being exchanged, okay, you permit me to bring forward our professor, Professor Abolari, as he gives his goodwill message for this event. You are welcome, sir.
Good morning, the Vice Chancellor, ably represented by our dear librarian of the university, Professor Isaac before I want my Dean of Science, Professor Ajiboye, you are welcome. I greet and I salute our Director, Professor Falabi Manu, our guest speaker, Professor Iyiola, you are welcome. HOD, Professor Iyiola, you are welcome. And I want to greet every other person here. Thank you for honoring this great occasion of this mathematics at your doorstep. Mathematics at your doorstep. It has been my yearning to see how we can bridge the gap of people that have phobia for mathematics. And to be candid, you see that everybody is now rushing for mathematical applications now, which is now helping us to bridge the gap of that phobia. You see mathematics becoming reality. Now we can use mathematics in the library. We can get your data and help you to analyze what is happening in your library. And in almost every field, whether in business, like somebody works in the financial mathematics, economy, like I tell some of our students, you want to do projects, you can easily go to different areas. With the modeling, economy problem, even politics today, you should begin to have somebody working by applying some models to politics, to Nigerian politics that is so special. Mathematics is being used in health sciences and all that. Even many are modeling the blood flow in your body, the heartbeat, and so on and so forth. So mathematics is now becoming the pride of every profession. And more especially, I want to thank Professor Bakari for bringing about this kind of great thing. Many of you are seeing this happen today. It is not something that happens suddenly. It is always a result of a long time of burning candle in the night. At least I know a little of it. I know how we have been so much engrossed with bringing something out of mathematics. At least for more than a decade now. It's almost lost into this thing. Indeed, I am so proud of you. I remember when I was inside of the department, we discussed. See, I want to go for social conference. I must do to go. Because when you acquire something that I know, whether we like it or to be a benefit to the university. And today we can see it. And I want to encourage every one of us that are here. That mathematics is so robust that you can dive into different fields. Especially you people that are just coming up. We have more than enough areas of mathematics to do research in that can be applied to real life situations. And you can easily collaborate with many people, many other fields in biology, in chemical, in industries, in commerce, and so on and so forth. So it's a great thing that we are doing today. And on behalf of my colleagues in the department, we are telling you that we are sincerely happy to see this program coming up. And we are sure that very soon some other ones will come up. In fact, there is more now than one see, and that is the area of excellent mathematics, trying to bridge a gap between natural mathematics and other mathematics. Many people are running away from pure mathematics today. But we need to begin to discuss it. We don't know the answer of that fact. I don't know what to look at. But there must be a bridge between the two so that our students can do it. Thank you so much. On behalf of all of us in the mathematics department, I want to welcome you to this great discourse. We are sure that we are going to do something tangible today. Thank you very much. Enjoy your week. Thank you.
Thank you so much, sir. You know, I picked that last one. He said, on behalf of the family of mathematics, so I am very happy that you know, we have, like I said, it's a full house, right? We have the backing department, the faculty, and the university. So we can keep on going, right? All right, thank you. Here in the crowd is also one of our distinguished lecturer, senior lecturer in the department, for that matter, the coordinator of the department, person of Dr. Maduaka Chika, who came in while Professor Olaniyi was speaking. Please, let's bring her to the high table. Thank you, thank you, thank you. We are happy to have you back.
Welcome to High School.
That is not like the name of the person we are introducing. All right. One of very respected professor of the department also who is going to bring us a goodwill message, like I told you before. So we are the one who bears the name of my director also. So wherever I see this name, you know, I respect this name. Professor Emmanuel Adeyefa, please, let's put our hands together. Keep clapping until he comes here. Welcome, sir. The Vice Chancellor, represented by Professor Iyiola, our guest lecturer today, Mr. Iyiola, you are welcome, sir. The director, Kamda, my HOD, I'm sorry, the dean, the professor in the department, Mr. Bolari, my colleagues, participants from outside and within the university, all our students, I greet you all. I use this opportunity to congratulate and thank our director for this privilege. Actually, when it comes to mathematics, in some other people outside, they thought that math is drowned. Is it that they are doing there? But today, I want to believe that every one of us present, we are going to have this program as eye-opener to see that mathematics is applicable to the real world. And the grace of God we had in one of our students in Louisiana University, and there this time that it just sent a letter to me. And when I read, I posted to the platform of the department. The US wanting to combat insecurity, and they wrote a letter to this university, Louisiana University in the US, and to the mathematics department, looking for mathematics students who could write programs to combat insecurity in the US. For you all to know the importance of mathematics in our real world. We are here today to witness application of mathematics to our real world problem. And as you have come, I wish everyone a peace day. God bless you. And so, straight forward now, we will be going to the speech from the Dean of the Faculty of Science. Please join me as I bring up to the podium Professor A. Ajiboye as we have a message from the Dean. You are welcome, sir.
Vice Chancellor, ably represented by Professor Isaac Usayo, the invited guest, Professor Olaniyi Iyiola, the director of the CAMDA, the HOD, mathematics, all professors in that department, all lecturers in that department of mathematics, distinguished ladies and gentlemen. I welcome you to this important program. I wouldn't have come at this time. I would have been here when the program started, but today is also the matriculation of our students, 100 level students, so we have to be in phase 1 and do that. So, I don't have much to say, but what I want to say is that the Department of Mathematics has been projecting the image of the faculty in a very good light. And also, it has also brought the faculty researches and collaborations to global map. So I'm proud of that Department of Mathematics. So, and I know this cannot be achievable without the contributions of those people that are seated here. And especially I want to thank the director of Nkanda, Professor Afolabi for a very wonderful job that he's doing in that center. This time I have it on the platform that is bringing maybe seminars, organizing seminars, workshops. I'm always very, very happy that this man is doing a very great job for us in this faculty and of course in the university. So today's program is a very, very important program. It's the way to go for us. Scholars that are just coming on board. We are cross-breeding ideas. We are cross-breeding knowledge. So we can tap from the experience or the experiences of those that are in the position to dish it out to us. So I know by doing so,
so well, I just prepared a little thing here, which I will just read through because of our time. Having recognized all important dignitaries here present, I want to go to the speech that welcome you all to this one-day seminar organized by International Center for Applied Mathematical Modeling and Data Analytics, CAMDA, in conjunction with the Department of Mathematics, Federal University of Nigeria, on the topic Generalized Numerical Solutions model by Prof. Iyiola. You are welcome, sir. Thank you for honoring our invitation. All the way from Morgan State University, Baltimore, Maryland, United States of America. The program organized by the center is what we need at this time to forge ahead in research and collaborations. The faculty and the university at large are not unmindful of the significant contributions of the center, in training young minds in science and mathematics and other aspects of human endeavors, making use of legal resources available at its disposal. Ladies and gentlemen, I welcome you once again to this great academic discourse. I hope we will learn and gather new ideas and experience hinge on innovation and transformational character. Today, I wish to sincerely appreciate the Center for serving as a platform to bring scientists across the world together to deliberate and research on some common values that are needed to be added to scientific contribution in mathematics or mathematical modeling. What we need as scholars this time is to move ahead with time on global map. The center is playing a pivotal role in this regard to foster unity and progress among colleagues that are deeply interested in bringing development to our dear nation through research and collaborations. Ladies and gentlemen, I wish you pleasant research celebration. Thank you.
That is our team. Thank you so much, sir, for trusting in what we are doing here and coming here to really cheer us on. We are very grateful, sir. God bless you, sir. All right. Now, if you happen to have the program with you, you will know that we'll soon come to the end of the first half of the program where we'll go for our tea break before we come in for the main business of the day. But before we do that, you have been hearing about Ikanda, since the beginning of this program. So we just want to say a little about Ikanda so that you take that away as part of what you take away from this program. And so this is going to be delivered by the director himself, the director of our center, the International Center for Applied Mathematical Modeling and Data Analytics, the person of Professor Afolabi.
Bakari. You're welcome, sir.
Thank you very much. We want to, still standing on the existing protocol, we want to give a brief, a short discussion on the center, what we do, what is it about, and then whether it can be useful to you what we are doing. So, can you suppose the next thing, please? Now we have the outline about us, what's our aim, our objectives, and we have the list of trainings, and the activities, projects, and funding opportunities and collaborations. Now, the Center International Center for Applied Mathematical Modeling is an international center in Nigeria, founded in 2022, and is a member of the West African Mathematical Modeling Capacity Development that involves Anglophone, Francophone, Lusophone, and partnership. Now, the campus mission is to improve health in Nigeria and Africa at large through epidemiological modeling and analytics. Our research interest is mainly in the development and application of mathematical, statistical, and computer simulations to understand and predict or project the dynamics of transmission and control interventions of infection disease to evaluate the impact of optimal policies aimed at reducing morbidity, mortality, prevalence, and incidence. The campus research has researchers trained in mathematics. We have people from maths, so our focus is multidisciplinary. People from biology, physics, statistics, computer science, epidemiology, and other relevant fields who bridge disciplines to understand disease dynamics and improve real-world outcomes. Now, this involves tackling complex health scenarios and developing tools that allow decision makers to navigate uncertainty. Now, the center's research is closely integrated with various disciplines, which results in policy-driven and impactful scientific research. We work with a wide variety of health issues that includes malaria, NTD, that's neglected tropical diseases like schistosomiasis, leishmaniasis, and soil transmitted meat and all the likes. Lassa fever, vaccine preventable diseases like diphtheria and cholera and lots of them. Imagine and reimagine infectious diseases or public health threats. We are deeply interested in the use of mathematical modeling in evidence-based policy decision making. We are part of Malaria Modeling Expert Group for the National Malaria Elimination Program. So we are actually one of the national, this center in Oye is recognized, and we have a letter to that effect as the National Malaria Modeling Consultant and Expert Group for Federal Ministry of Health. We are in research, training, networking, and services in applied mathematical modeling and analytics. We are also involved in academic and operational modeling of health and diseases. We consult for NCDC, that's Nigerian Center for Disease Control and Prevention, NMEP, National Malaria Elimination Program, WHO, and the Malaria Consortium, and several other public health agencies in Nigeria. Okay, so our WAMCAT Consortium involves West African partners, which comes from University Oye-Ekiti in Senegal, those are the Francophone collaborators. We have University of Conakry, Guinea-Conakry. We have people from Berlin X project in Guinea-Bissau, and that is in Lusophone because they speak Portuguese. And then we have University of Ghana and University Oye-Ekiti, which are the Anglophone part. And then we have the partners from the north, which involves Northwestern University, Malaria Consortium, SWISTPH, Oxford University, and PATH. And the aim of the Gambia is to provide a platform to build mathematical modeling capacity in Africa, particularly Nigeria, in a holistic and self-sufficient way by exploiting every available and genuine means. Objectives: we provide internationally relevant research in the field of mathematical and statistical modeling for disease. We develop and implement mathematical and statistical models to address contextual relevant research questions as defined by programmatic and community level stakeholders. So all of our projects, starting from masters to PhD, they are given by the Federal Ministry of Health. All the questions the PhD are answering, they are questions that are given by National Malaria Education Program. So it's not a question that's going to be kept. Every month there's an update that this is the way to do this, is the way to do that. This is kind of what's it called? The model is saying that we should provide social number of nets and all of that. That's the kind of work we are doing. Now, provide research community for mathematical and statistical modeling for quantitative support for researchers at all end sectors in Nigeria and Africa at large. We also like to contribute to the development and implementation of institutional-based approach for data management and effective sharing of modeling and quantitative research products. We are also interested in investigative methods to enhance modeling and quantitative research capacity among public health researchers and practitioners in developing countries, particularly Nigeria. Support decision making and policy development in Africa, particularly Nigeria. Now, capacity building also, we organize workshop training, which is one of these, in different parts of the country, in mathematical and statistical modeling in Nigeria and other African countries. Encourage dialogue with public health experts on the use of data analytics, mathematical and statistical modeling with computer simulation in guiding policy and disease management. Now, we have some trainings now who are working on different topics, which I did not be able to mention everything, but we have postdocs and past postdocs. So there's somebody from Federal University of Technology, Akure, who has been with us for 2 years. That's Dr. Abidete Afix. He's been on postdoc here, even in Oye, Federal University Oye-Ekiti, and he's been working on modeling the effect of seasonal malaria level prevention and R21 battery, that's the vaccine, the latest vaccine they are deploying in Nigeria this November, on the dynamics of plasmodium malaria transmission in Nigeria. We have had somebody who in the past who has worked on modeling the effect of control intervention, compliance rates in the plasmodium malaria transmission in northern Nigeria. And presently, we have a female postdoctoral scientist, Dr. Iyiola Olaniyi, who is working on modeling the effect of ACT-based treatment strategies for malaria transmission dynamics in high-body states in Nigeria. And the last million performance who have worked on those topics from Computer Engineering, Federal University Oye-Ekiti. We have also had Dr. Lawrence Bumi, who are in the past who have worked on machine learning aspects of the work. Now, presently, we have some PhD students, PhD scholars, not only from mathematics. We have PhD scholars, Mr. Okodui, who is working on modeling the effect and risk of seasonal thermal prevention. Mr. Olashiko Idowu, who has been our MC, who is also working on modeling the effect of some vector control intervention on the dynamics of PF malaria dynamics in Nigeria. Now, we have somebody also from computer science. We are working with computer science department, and that's why it's a multidisciplinary aspect. That's Mrs. Iyiola Olaniyi, and then we have Oshikoya Samuel, who is also working on malaria transmission dynamics in low and high body settings in Nigeria. We have somebody from parasitology. We are working with Professor Yedeji, and together to train somebody in parasitology is Mr. Wana Aaron, who is working on modeling so there's a modeling part and there's a parasitology part, and we are bringing the idea together, modeling the molecular markers of PF malaria, antimicrobial resistance, ACT treatment, and treatment failure in selected Nigerian states. Now we have somebody also from electrical engineering masters who is working on modeling the effects of climate factors on the effectiveness of ACT and NLI in the University of Mr. Stephen. And Ms. Happiness is also from AEB, who is also working with us on the modeling effect of presumptive and test-based malaria treatments on malaria prevalence and transmission dynamics in selected local government areas of Ekiti State. Now we have other joint collaboration with some other students. Now we have had internship students from Akoma University, from that's Karis Akobi, testimony of Obalade, computer science and economics of Afemi Awolowo, Samuel Ayoride from AIDS, Cameroon, that's African Institute of Mathematical Science, Ademola Adebowale, who has been with us for the past 6 months. He has finished now from Achievers University. We have also trained close to 20 students from mathematics department on GIT, that's graduate internship training with scholarship for 3 months, both feeding, accommodation, and students. With animal, with people in agriculture, there's a particular work that we are doing on cassava mosaic, and part of the trainings we have done, spatial data analysis and Bayesian modeling. And then we have also organized training on geospatial modeling and all of that. Now, many people that benefit from all of this. We also build modeling into national programs. So presently, we are interested also in training people in public health. So we have organized a curriculum at the national level, which we went to Abuja on Monday to talk about. From next year, we training lots of medical doctors who are in public health at the national level from Federal Ministry of Health on modeling, on how modeling can be useful in prediction, maybe during outbreak and all of that. Like during the last COVID, we were part of the modeling group for Nigeria, predicting and showing some data on how the use of non-pharmaceutical intervention. Now, we connect modelers. We are part of a formal network to connect all program participants across the 5 sites, which are Senegal, Ghana, Nigeria, Guinea-Conakry, Guinea-Bissau. We are already a member of Applied Malaria Modeling Network. We have Ahmed Nigeria national headquarters located in Foye. Now, we are being funded presently by Bill and Melinda Gates Foundation grant of capacity building of malaria modeling and analytics. And the project is also being extended, I think, in 2027, the current thing we are hearing. Now, then we have other projects from UCH that has to do with mental health modeling and analytics, which we are also involved from 2024 to 2017. And then we have the malaria modeling fellowship, capacity building, modeling, malaria in conjunction with NMDP. And then opportunities and collaboration. So there is room for internship. I mean internship, you go online, that's our website, and then visiting scholarship, like you go from basic, intermediate, and advanced training in modeling and analytics. We also have regular association. You want to come and you want to do some work, you can contact us, and then you can also train and give some light to whatsoever you want to do. Ongoing plan for PhD and MSc in modeling and analytics. Now, acknowledgements, Big Data Institute, and all of that. And then, in the recent time, we want to also appreciate the Vice Chancellor and the management have given us the opportunity to have our own land and our own building. And we have been given the land to build our own structure in the building. So, thank you very much. Our lab president, we are trusting God that we are going to have something bigger than this. Thank you.
Well, let's give an innovation for the work done so far by our professor, the visionary professor for that. invested in himself so much and is transferring it to the upcoming generation. And we are happy to really be part of what is going on. And we can only say, God bless you, sir. We are grateful. All right, thank you so much. So that is the website of the Canada, and I should also announce to you also that come December 9 to 13, we are going to be having one of our outreaches to Lasso Tech, which is going to be the school, modeling school, our second modeling school. So we normally have outreaches, to universities. So this outreach is going to be to Lasso Tech, and the application is currently on. You may want to take advantage of that opportunity. All right, and all our programs, most times sponsored and then well packaged. Thank you so much. Okay, so now we need to rest a bit. We have been sitting down since morning, so we just like to have a light refreshment, walk around, see, look at your back, see there is something you need to pick, and then eat and talk. All right, so all right, before, okay, yeah, our Vice Chancellor ably represented by the librarian, is about to take his leave, but before doing that, he has something to say to us. So please welcome again with me, the librarian. Welcome, sir. Okay, sorry for that. I am just informed now that another professor, respected professor of the university is around from plant science, a person of Professor Akolade. Please help me bring him to the high table. Bring him to the high table. All right, so let me bring the librarian to speak to us before he takes his speech.
Distinguished members of the high table, ladies and gentlemen, the speech of the director cannot just come like that and go without being acknowledged. If I were to mimic the VC, I know if the VC were to be here, and I've heard him say it severally, that Professor Emmanuel Afolabi Bakari is a man that everybody is pleased with. The VC will say, it's my man, in whom I'm well pleased. And often, the VC will say, if we have just 5 of the likes of Professor Bakari on this campus, that 4 years will not remain the same again, considering the number of grants that he has attracted to the university. I know with God on our side, Professor Bakari will replicate himself, because he's already doing that. This workshop is a prelude to that. And I know that before long, you will begin to see your products. And I know that the sky is not your limit, but your starting point. God bless you all. I have a successful conference.
Sorry, we would like to just snap with the VC before he steps out. Please, the people on the high table, so we just, with your children, we just stand before you here. Maybe you need, please let's come around, as many people who can find somewhere. So please, let's just snap with them. Thank you. Come to front, and then we'll snap with them. People seated, please, you can also, yes, they will first snap, and then later the rest of us. So we can snap here. Let's snap here because of the backdrop. Let's snap here because of the backdrop. So we can come to the president. Okay? So you realize that in the left terminal Oye-Ekiti is just of 6. Who is standing? Who I'm standing by? I'm standing by because I also will become a professor. So please, I want us to just move our hands together as we welcome him. You are welcome, sir. All right, please, let's go for our tea break and then come back for the main tea. The tea break is just 15 minutes. Break is just for 15 minutes. So go to the back. We direct you what to do. Thank you. Please get visited. You also have to direct us.
Yes, your brother.
Thank you. You know him already now.
Dr. Iyola's educational journey began with a bachelor's degree in mathematics from the University of Nigeria in Nsukka. He then pursued a master's degree at the African University of Science and Technology in Abuja, Nigeria. His academic path led him to the University of Wisconsin, Milwaukee, where he had a PhD in applied and computational mathematics with a minor in probability. Later, he proved his expertise by obtaining an MBA in data analysis from California University of Pennsylvania. Currently, Dr. Olaniyi Iyiola holds the position of Assistant Professor of Mathematics at Modern State University in Iyiola. His previous roles include Assistant Professor positions at Clarkson University in New York, California University of Pennsylvania, and at Minnesota State University. Throughout his career, Dr. Iyiola has received numerous accolades. These include a Faculty Service Award 2024 from North State University Primary Department, recognition for outstanding teaching performance in graduate level courses from the Dean of Arts and Sciences in 2021 and 2024, and a Merit Award for Research in 2020 from California University of Pennsylvania. His research has also received significant attention, with one of his papers being the most cited since 2019 in applied numerical mathematics. Additionally, Dr. Iyiola has been ranked among the top 2% of scientists worldwide. And others in 2022, 2023, and 2024, the Stanford University compilation used the Elsevier database. During his graduate studies at the University of Wisconsin-Milwaukee, he received the Lawrence Technique Award for Outstanding Research Potential in 2017, and the Morris and William Award for a quality research paper in 2016. In the realms of nonlinear optimization and numerical analysis of non-integral differential models, Dr. Iyiola has made noteworthy scientific advancements. His outstanding research achievements have gained in worldwide acclaim, honors, and strong collaborative opportunities. With over 85 interdisciplinary peer-reviewed articles published in regarded journals in his field, Dr. Olaniyi Iyiola has demonstrated impressive scholarly productivity. This publication has received more than 1,000 citations to bodies metrics, resulting in an H index of 31 and I-10 index of 72. Dr. Asamoah Okwanta, the mathematics department chair, and Dr. Andrew, the provost, have nominated him for 2 prestigious national awards. The MIC National Award for Young Scientists up a $250,000 prize, and the Waterman Award, which comes with a substantial $1 million monetary value. The optimization keyword with 21% acceptance rate. Dr. Iyola's publication, new projection method with inertial steps for variation inequality, and it was written in the past 3 years throughout his professional journey. Dr. Iyiola has a strong connection with scholars in his research areas across the globe. These partnerships extend to various countries, including the United States, China, Israel, South Africa, Vietnam, France, Saudi Arabia, and Syria. Is notable collaborators are Dr. Iyiola Olaniyi from China, who has accumulated 6,000 citations in scopus, and Dr. Rich, Professor Emeritus and pioneer of non-linear optimization in Israel, with up to 50,000 citations on Google Scholar. Furthermore, he has worked alongside Dr. Iyiola from Lincoln State University, whose work has garnered over 1,000 citations from Google Scholar. Dr. Iyiola's research interests are in numerical analysis, algorithms and analysis of differential equations, integral and non-integral model, computational mathematics, simulations in applications, building model optimization, data science, data analytics, machine learning, deep learning, and artificial intelligence, mathematical biology, and non-linear operator theory, involving fixed-point algorithms for solving variational inequality problems, optimization, equilibrium problems, and non-linear integral equations. Dr. Iyiola extensive experience in formulating optimization models in both finite and infinite dimensions. His current research involves the development of new types of iterative schemes for optimization problems that capture complexities of real-life applications. He also has experience in developing numerical algorithms for solving non-linear problems with complex domains, including equations that are numerically unstable unless the step line is needed to be extremely small. Dr. Iyiola is an expert in data mining and machine learning with skills in SNS from FQL, JNP, MATLAB, mathematical, network, of services. Dr. Iyiola is currently one, the chair, academic and student affairs, Modern State University Council. He is currently the chair, Comprehensive Examination Committee, Department of Mathematics, Modern State University. He, the chair, Comprehensive Exams, Department of Mathematics, Modern State University. Or member of the Program Admission Committee, Department of Mathematics, Modern State University. 5. Member of the Students Advisement Committee on the Development and Values, Department of Mathematics, Modern State University. 6. Is the Director of Department of Mathematics, Modern State University. 7. Manuscripts for reputable journals, monthly work, and future SMJ revenue. 8. Is member, fixed-point methods and optimization. Student of Prof. 2024 to date. 9. Is editor, statistical and computational physics section. In physics 2022 till present. 10 is editor, trainer of non-linear evolution equations and applications, Junior 2022 till present. 11 is editor, fixed-point theory section, in applied mathematics and statistics, 2020 till present. 12 is editor, symmetric, special issue, new trends in national calculus and applications in engineering and infection diseases that was 2020 to 2021. 13 is the competitive editor, fractal and fractional special issue, calculus and its application to arbitrary time scales 2020 to 2021. Editor, one theory, Mathematics and Statistics, 2019 to 2020.
Like the director for invited interest. I like the like the fact that right here is a total only to be here. I look at likely is I was not likely I was going to find I spent if I had 2 days in the United States, so I now the time will be spent on present here. It is really all about saving the whole time. When it was invited, I just is going to be a class with this new visualization. I think it was going to be still in other words. You believe all that. Since I left the country, my passion is always to reach out and make more movements. I think how so many teams and I'm only thinking this. Most of them reach out from me. Lately, I tell them to do it. Yeah, they are some of it on the PhD or everything, and so on. But I think they have the PhD. Few of my students are from Nigeria. Few of my PhD students are from Nigeria and from the rest of Nigeria. And when we talk about again, I was like, this 50 years ago, but something to instead. Because most of the opportunities out there, most of the things you need to do to be successful is all about the information that you are getting. So the more information you have, the more you are able to address those opportunities. Because I'm going to be talking about something I've been waiting for a while. I think I started working on this in 2001. And I know we have the graduate students here, different levels of students. If there is any electricality that we are not started, you can talk to me after, but you can reach out to me. And of course, once you do the finding, you will create some of the big outside this product. So, the more the presentation is going to be on generalized differential equation. It's going to be talking about numerical solutions and application. And I want to use this opportunity to also have to university to actually solve the track methodology. I'm going to follow this argument. I'm going to talk about the review overview of the research, the motivation for something called fractional accountability. You all know that generalization of that, and some of the network efforts. I'm talking about applications. I'm talking about some challenges and And particularly, if you are working on something that is related to this, we people always reach out. All right. So I can categorize my research work into three categories. Most of that is fixed point algorithm, where we develop fixed points activities to solve various problems. When I got introduced to fixed points in 2008, usually it's not about proof the theorems and postgraduate. So when I got to PhD, I started on analysis. Was one of those that started applying this algorithm to solve real problems and connecting it to very state and very applications. So one of the things that the problem applying this to breast cancer application. Data science is the point there. Like you had from the solutions after the PhD, I decided to go back to our data analytics and apply other skills in data science. So I'll be working on areas of data science, machine learning, artificial intelligence. And the goal is to use it as tools in analysis, right? It's not just to get the data and do the statistics of it. I want to see where, for example, this point that Lori did can help you to make the best choice of the weight, right? We are doing the machine learning. There is very important relevant algorithms. So they are rapidly generated. That can affect the performance of the prediction. So you can actually use fixed points calculation to select that weight and optical weight. And of course, the third one is the differential equation. I started my journey in differential equation from the theoretical point of view. I worked on several spaces and from the view was that existence, uniqueness, stability, and all that. Then I know people believe so I like to solving them with very good results after developing that methods. Why the subject called fractional calculus? I remember it was in 2010. I got to AUSC Abuja, and there was a professor that to teach fractional calculus. I was like, what's it about? The short answer is usually you have first order derivative, right? Second order derivative, third order derivative. The question is, what is out order derivative? What is 3/2 order derivative? When it is not 80. But before I go to that detail, why do we look at all this? Why do we need practical calculus? It has found application in mechanics, for some of it application in mechanics. That has to do with viscoelasticity and viscoplasticity. On chemistry, modeling of polymers and proteins, after taking them and further position. So when you see animals with patterns of them, right? These patterns are more chemical reactions that are done. And we can use that as the models of behavior. And so we'll see how fractional calculus is. Electrical engineering, medicine, mathematical psychology, control theory, genetic authority, functional and data, data analysis, contaminant flow, modeling of memory, dependent, phenomenal, learning of complexity. All right, let me show you some good examples of what reaction diffusion. I just told you that patterns usually are caused by some chemical reaction in the atmosphere. So the first picture there has to do with cell division. You have a single cell, you break it into two, breaks it into four. That's the normal process. These are being captured using reaction diffusion. And then we have it, right? And then fish up. So some of these are well on to be captured by a model called reaction diffusion. And also, this is another interesting biological pattern that you can capture using reaction diffusion. The spiral measure, the different type of patterns that are nature. Samples also can be captured using reaction. All right, so think that we can capture something using reaction diffusion. The problem is, you see that visually this particular system, and then you suddenly see another on the same time, have a different pattern. Or maybe the pattern, let's say spiral, and then you see an elsewhere having several spines. And you are looking what is way. Or evaluate where cell defines equal 2 equal 4. That's the format process. Some cells can take longer time to complete that process. Some cells can take shorter time to complete that process. Some cells can even have abnormalities in that process. For example, you can have a single cell breaking into 4 directly without crossing the arista. We can have them using the various, not following the order. And also, when you take a medication, right? You take the medication. Some medications will take so much time to digest your system before it goes to. Some medication you just take is like this, it's in your system, right? So that process I just explained is what we call slow dilution and fast dilution. And I'm going to tell you how we use fractional calculation, because then you have the order, first order, second order. How do you explain that order to capture various situations? That's the problem. So can we use fractional calculation? All right. Fractional calculus came in 2 ways. There are some group of people who say, mathematically, does it make sense to have fractional order? Right. That's the kind of mathematical curiosity. And so once you come with that idea, you want to find the sign here. And there are some other school of thought like this. I did something in my lab, and I did something that does not follow the regular models that we have. How do I explain this? So that's how we find mathematics to justify it. All right, so let's make a little story. In 1695, of course, Leibniz developed the X order derivative, right? First, second, third, and so on. So Leibniz wrote in the letter and said, this X order, when N is armed, no without it. And let this reply, I said, it will lead to the paradox from which one day useful consequences will be drawn. That was his reply in 1695. Just to answer the question, what happened to F 1/2 derivative? Just that question. Okay, everybody know Euler, right? Euler developed the gamma function. We have talked about gamma function before. And so, right. Now, when you have x to the power n, you can write it as x times x times x up to x time, right? And you can write that as b to the power n log x, right? These are literally true even when n is not integer, right? So, in other words, we have generalized things from integer to non-integer without paying too much attention to it. Also, when you have factorial, x factorial is actually gamma of n plus 1. So you move, but gamma function doesn't have to be integer. The s in that integral, right, doesn't have to be integer. So if I can connect factorial to gamma function, I can generalize factorial is for integers with gamma function, which is for everything. With other that. Having this understanding, Euler said to answer L'Hopital's question. That was in 1730. So he published this paper, and he concerned about the monotheist. The monotheist is just like a power function, right? So he was curious to say, okay, let us know confinement x derivative of the monotheist is given by that formula, n factorial about n minus n factorial x to the n minus n. But look at that one carefully. The straight thing here in the factorial, right? And since I know how to move from the factorial to gamma, which now has a generalized input, we just converted those messages. This converted the formula into gamma function, and that's it. So he's able to write the alpha derivative of the function. The moment you read this one, his goal was to find the formula to find the alpha derivative, right? So first, we plot the alpha. And then we got a formula for that. That's it. So we got the formula for that. So alpha derivative is given by Euler is now 2 square root of x over pi. So if you don't remember anything, I will just remember half there is that was Euler. And then, as it was being celebrated, everybody sat back and said, okay, let's take a look. And oh my God, the derivative of constant is not zero. If you plug in the constant into that formula that was in the previous slide, the derivative is not going to be zero. It's so we got very nice before, but it doesn't follow the classical approach. It doesn't follow, everybody wants derivative of constant. So that was where it stopped its work. But remember, until this point, everything he was talking about or he was dealing with is to find the half derivative of the moment. So later than later, if you don't know some of these things, I'm calling one of the greatest competitions that we have. Okay, so if I have x integral of the function, which is given as multiple integer, this way, you can prove that this formula can be written as a single integer with the factorial of 9 probability. This is, we can do this induction proof is straightforward. Now, rather than waiting, we said, okay, using the idea of Euler, all I have here is factorial, and they are giving us the power to come factorial to Java. Just convert 1 over n factorial. N minus 1 factorial, remember n factorial is Java of n plus 1. So n minus 1 factorial will be Java of n, right? But as long as present is just n, and present in alpha, which is n for right? So the label will be formula in green. So instead of 1 by n minus 1 factorial is gamma over gamma. And that is what we establish and what is called the unlimited fractional integer. Because the order here is not just integer. So if I have an integer, what's the natural question? What's the derivative? Right? And if I have a derivative, I want to be sure that the derivative of an integer is an additive. So if I want those things, how do I naturally look for the derivative of this integer? So, okay, so that part is just to be the proper definition of the value of the integral, because you have to make variations at value. So, naturally, so I have a term, I write this term as V N I N N. Right? N is still classical derivative, right? Integer power derivative. D represents the derivative operator, I represent the integral operator. Now, if I have that, I forget about the first part, I forget about that, I go into the beginning, and I separate I to the n into I to the n minus alpha times I to the power. So now I have four components, dn, I to I to the n minus alpha, I to the alpha, and n. So split those things into two. You have I to the alpha of there, right? You have dn, I to the n minus alpha, and the left. And naturally, if you take the left half as your derivative, it will recover n. So that was what the really. And so naturally, they want to find the derivative, what is already limited derivative, or limited fractional derivative. And if you do that, right? You quickly want to check what has been done. So the check the formula that Euler produced, right? Which is so they got this formula and they gave them exactly what formula plot when it's more for their own for general. So this was then corrected because it doesn't naturally. But what's the problem? Of course, if this is generalized Euler, the derivative of constant is not zero. It's a problem. What's much more, right? What about some things speech about how to solve differential equation and equation of what. So when that differential equation is what we have to look at all the way to its like everything. Unfortunately, if the Laplace transform of this operator, this differential operator, everything seems to be right until you get to the square. You see, normally, in the regular Laplace transform, the sum does not give you the, you see there is a derivative next. You don't have the derivative, that's starting. So, it means that you have to get the derivative of the initial condition. The initial condition has to be given in terms of the derivative, which is really what we don't have that. So this is another drawback of this definition. So because of this, several people came up and said, okay, can we modify this definition so that we can enjoy the properties of some of the classical properties, some of the classical cases. So that people came up, your people came up, in fact, came up, which much happy of. I'm going to talk a little bit about this. So for our people, this is an engineer and he's still alive. So he was working in the engineering field and came on with this integral. I realized that this integral is some kind of fraction. Right? Look carefully at this integral. You will see that the difference is that in the previous river, we differentiate the integral. That's something to dl on I minus answer. How we find the river? Here, you are integrating the derivative. The derivative is inside the integral. This state. That's the only difference of the sums. Okay? And of course, if you take some very nice functions, you can find the relationship between the capital and the debit. The good news in this one is that if you take the Laplace transform, you get the classical case. And the derivative of constant is zero. The derivative of constant is zero. Because look at the integral and the derivative before you get it zero, right? So, so if I can block the so let me start with if I get the same definition this way, I'm sorry, this is very good time. But the goal of paper is to interpolate the different paper and between reliability and completeness. So this definition, when you set beta to be 1, you will get completeness. Derivatives. If you set beta to 0, you get verbal derivatives. So we call this interpolation in favor of capitals. So it's a bit general. All right. Now, everything that we're talking about is difficult to do numerically. If you have done any numerical concept, you start with final difference, right? This is our favorite, the limit definition of the derivative. So the question will be, can I have a form of linear definition for fractional derivative? So Prof and then came up with the definition by form limits. And up to today, most people who want to develop numerical space, especially limits. So we have fractional this fraction, which is in terms of Fourier operator and the universe. And we have this and that integral, sometimes involving this. So most of our papers are is in detail. If you want to make it, I'll take it. And so that's just the formal definition to see that this is actually the combination of left and right and equally village derivative. And of course, recently there was the new generalized operator called side fractional integral and side fractional derivative. So the idea is to remember from labor inside the integral, if that side prime is to get the side, it's not the sine of t is t, sine of x is x in the previous definition. So the idea is to introduce the function which satisfies the condition that we said there in a way that we can now have something more general. Right. So we have left and right. Like that. Of course, this satisfies some what we call certain properties. So that was the integral. So the derivative of it is given this way. Right. And if you take some special cases, this actually generalizes. I listed about 5 or 6 here, but there are several fractional derivatives at this point. So it's very, very close to the final fields. For example, to take beta to be 1, and that side of t to be t, you get a calculated fractional derivative. If you take beta to be 0 and side of t to be t, they get a value equivalent. If you take sine of t to be t, with the integral case, you get the calculated fractional integral. Right. If you take sine of t to be t at a to be you get what we call the fractional integral. Note that the endpoint is not as t for this particular case. Right. If you take sine of t to be the power function, you obtain what we call calculated fractional integral, which is fixed. Right. Of course, if you take sine of t to be t and a to be negative you get the mean fractional derivative. So I just listed a few of them. And if you go to the next slide, I gave some examples of the special cases for the derivative case. So this is extremely general. So if you want to do it to the field of fractional derivative calculus, and you feel that you want, so most of the previous definition are exhausted many ideas that if you take on this book, you have many things to do. However, most of the analysis you have to be there, because now you find not in the general society. Instead of just leave on this. All right, just as I said before, and balance dilution as needed. So, what happened? Look at that equation. This is stable heat equation, right? Usually, what we have is constant time every second space, right? So, if you put beta in time and alpha over 2 in space, if alpha is between 0 and 1, and pick the alpha, sorry, beta is between 0 and 1, and pick alpha to be 2, the right hand side is the classical fraction, but the left hand side is time fraction. Negative. So, in this situation, we capture what we call slow dilution. The process that is very we can capture it in that next. Of course, when we have beta in power, alpha is 2, that's the normal dilution. So when we fix the delta, we let alpha go between 0 and 2, we have what we call fast dilution. Take note of all these cases, especially the ones which are making talk about. All right, so if I want to solve a PD, right, partial differential equation, I need to develop a very rapidly. Or not say, I want to solve all kind of differential equation, develop a very rapidly. And so, remember I said, mathematical definition is usually used to develop, especially inference. So in 2006, Otakura gave this very useful step plan to equalizing fractional operator. So I don't want to bother with all the analysis there, but at the end of the day, what to get is that big lattice G. Look at that big lattice there. Okay. When I give the second order this equation, second order space, right? And you typifies it, what type of lattice you get? You will get a triangle in the base, right? There have to be numbers of the baby, that way the other constitutes, but that way is there will be numbers with the next diagonal entries. The rest will be what? 0. So that is usually triangle. When you are doing computation, of course, you have to multiply this by something, right? For finding the inverse. When you have a lot of zeros like that, computationally, your life is easier. Okay? The balance here is that when I'm doing the fractional derivative, I don't have zero anything. Everything in this gene is non-zero. Non-zero. So when I'm doing that computation, is very difficult. Very, very difficult. Especially if you want to do application. So one of the applications that I did has to involve 10 million by 30 of it. I can help to solve that. So that so people do application that market. Why they get that, right? If you have to feed in or grabbing over you want to solve, mathematically, we just take time to be 0 to 1 and we digitize it. Right? This is one of them. If I want to simulate processes, I get to just say it. So that's computation you don't need. You give you an idea of what is the dimension, right? If I now put it instead of 0 to 1, I can show you the top, I think up to 8,000. And so we might have the other points we have. All right, so in order to talk about the method of Iyiola, let's look at this simple looking equation. Okay? UT plus kappa Laplacian compactor by 2U equals to F of C. This is what we call reaction coefficient, space reaction coefficient. Why do I call it for fractional space reaction? Why do I call it that? Because the fractional freedom is not the space, not the time. Next. All right, so the issue is can I develop something called exponential prime really easy. Can I develop a time equalization scheme that can efficiently solve this type of problem? Remember that I'm going to be dealing with a derivatives, right? All right, so if I give you the PDE, we can digitize the space. And what we get is a system of ODE. So the digitization operator will be is actually a mistake. And that system is used ratio of constants. We have done that for ODE here. You get this integral. UT or U of t equals to exponential minus t times a U naught plus integral from 0 to t exponential minus 1 t minus a x f of 2x dx. So you need to solve this one, right? Because U is in both sides, you need to solve it. Look at that problem very well. We have two problems. Two. One, the function f is not linear. It's not linear. One is bigger than the challenge, right? Two, I have exponential matrix. That which is e to the minus PA is called exponential matrix. You want to find exponential of the matrix. That's very complex maths. Complex value. Even with a dry matrix. Now your matrix is moving. It's moving. All right, so those are two possibilities that we have to look at. How do we numerically find the exponential matrix, and how do we deal with the non-linear function? So, the stuff in the blue is just take the variable. Take the variable when you are solving. Numerically, you restrict yourself to the solve problem or solve the problem. T to T N plus 1, that's what I did in that equation down there. But we see our basic, we are still basing the exponential matrix and the linear function. Yes. So the first attempt is I can do the approximation. If you don't have calculus 2 or 3, then we are talking about linear approximation, right? If I linearize on n, it makes like this is on right. Because if I want to integrate the exponential of function n, but I don't know what n would be, right? But I have linearized it just substitute with the linear function, right? Now for the integrate, you don't figure the most important answer is integration like that because of the exponential. So when you do that algebra, you get what we call discrete equation. You get what we call the discrete equation. Now, in this equation, we have a lot of exponential things. We have a plus a. A lot of things are going on here. If you try to code this, you will be done correctly. Depending on what it is. You have the mean argue matrix exponential or exponential. In general, before this talk, people usually use something called Madej approximation. If you know the math before, we just using rational function to approximate the exponential. For example, if we use 1 over 1 minus c, we approximate into the c. That's what last one on the approximation. Right. And there are a lot of problems in that area. Now, there are problems with Madej approximation. One, the pole of the rational function will be complex. And then can get with complex number in computation that is very expensive. Also, it is difficult to do something we call partial fraction decomposition. When you have the fraction, I just split it into two going to be general. So the idea was to develop a rational function that has distinct poles, right? In a way that we have to split the function into two. Okay. So we want to write it in that form with 1 plus a 1 c over 1 minus b 1 c 1 minus b 2 b, where b1 and b2 are not the same, right? So that they have distinct poles. Not just that they have distinct poles, the poles are real. So I'm not going to go to having complex computation. Yeah, so we did some error estimates there. And so what about things you have to make your is that when you are doing numerical analysis or you are developing numerical data, there are two things that we can think about. One is what's called area acceptability. The other is what's called L acceptability. Don't want to go difficult with what I mean. But if your method is A acceptable, that's fine. However, if it's L acceptable, you will have more problems than the A acceptability. And so most people want to make sure that their method is L acceptable. Method that is L acceptable can help you to talk about what we call spurious oscillation with your solution to a problem is. You can get the method like that. Okay. So we prove that this approximation here is well accepted. I did that in 2007. And then with not so this method is second order. Okay. It makes sense to compare with second order method, right? So we just plotted the graph with exponential function, the approximation I just did, and three other or two other well-known data. I did 0 to minus 0 to 0 plus 2. That is the order. And the one is 1 plus 1, which is more than 2. So from the picture, you will see that the one in bottom is the one that just developed. It goes down a little bit, then we should have exponential at the beginning, right? So it goes down, it multiplies back quickly. The green one, which is the almighty particle, and this is not to be good. But we can see it is going away. And so that explains that mathematics is not affected. Yes. Okay, I don't want to hold you because of time. You plug it out, I gave we have a semi-discrete form of the scheme with many exponential matrices. Remove those things and plug in the rational function approximation that I just showed you. And do that, they split the fraction into two. Why did I have to do that? The good thing is that it allows you to do a lot of ultimate factoring things or binding things because of our business. If I do those things, I end up with a skill in that 6.1, which is called the corrector skill. Because if I'm a business method, I need to have lots of behavior corrector. Predicting with a simple error, and then use my statement correctly. Okay, so this is very nice. I have the method. We wanted an application that can be split into two. The rational function that I can do split into two. One of the reasons for that is that at the end of my scheme, I can generate something that can be done in parallel, which is going to speed up the lot of the conditional. Okay, this is here on the graph. Yeah, so this is the algorithm that we get from that, where you can do from work on process 1, you can do from work on process 2, and then combine the two of them together in the final state. So using the parallel algorithm is to can speed up. All right. I think we got from the analysis. Let's look at the application. All right. So the first application I'm showing here is response. We got biology, not biology, or we do probably we are familiar with response model. Response model is not to explain some biological findings. I'm going there later. If you are so much familiar with PDs before, look at this model. You can see it very well. It's a very big problem. It's a very, very big problem. You see the problem there? Perfect. So look critically at the initial condition. You on y, x, y is a radius from 0.5, where that condition is next, and that otherwise. That is continuous. That is continuous. That's a discontinuous function. And that's a big problem for the environment. We're supposed to have more of x or 0 with double sign x. Now we have a visual function which is not continuous in both cases. So some way that the point is struggle. Why do we choose this particular function? Or why do I choose it when I did before? One is very complex. When you develop a method and you're solving, using it to solve problems that are not so complex, you will not have advantage. So that's a good together of who are going to say. If I develop a mental skill, and then you go and think simple problem test with other methods. They will all go the same way because the problem is simply in the first place. So the goal is okay, to test your method, stop simple problem. Okay, with them. But to show the efficiency of your method, look for complex problem to solve. If you can argue that over consistently, then so that's one reason I chose this. The second reason I chose this because it's that application. Yes. And so I run the simulation. Okay. And I'm not sure if you can see very well. I showed the error. I showed the rate of convergence, which is supposed to be 2. So when you are looking for a second order, the rate of convergence is something close to 2, not necessarily exactly 2, or it will be 2. That's verified that the theory would be. Then I show the candidates. This is just for my method, not comparison, but I chose different alpha values. Yes. Now I compare this where you think. And there are 3 of them. And the 0 I showed you before, but the one I showed you before, and something called backward effects. See. So my speed is the black. Now, the possibility to be counted is the whole item that I've heard before. Then people like it because it's very, it's the blue. If I did 0 to the red, I'm thinking that 2 is the green. Now, I can make ground on the y-axis is impurities, on the x-axis is the error. The error started is 1 so I can stand. I'm not on this screen. It's very easy to show you. So, what's in your mind? Let's say there's something problem and you need just the error of 30 bars and eliminate. I don't want to. I don't want something that will be that we have too much error. So I need 30 negative 8. So if you stay on the course, so 30 negative 8 is the central exponent of the length. And that's 30 negative 8. Move your cursor on vertically left from 30 negative 8. With the same error, you want to say how much time will you take all the negatives. The method is smaller time is definition. So if you stay on top from that negative 8, which is just over the second backhand, move it on, you will hit the black line, right? Trace it to the left, that is set to the next set to 0. Right? So you will need 1 second for that. Continue moving it up until you hit the blue case. then move it to the right and to the left. That's about 10 to 1. That makes sense for granting also. Keep moving it up, particularly to hit the red. And then one more. It's only going to be set. That's 100% for PD magazine. And of course, PDM is 5. What that means is that I cannot get relevance. I have to pay these 2 steps in order to really match is happening to the situation. So the method is by you. The method is then the second application I'm showing is the model called Aging and People model. It is also a very valuable model. That's very very. I'm sure you are. Unfortunately, also, it has this continuous initial condition, right? Because this is one of the reasons why we get uncounted, right? You have to solve less or method, that situation. Yes. Of course, I like the same situations again, this is different numbers which is expected. Yes. The same now. So whenever you see people against the other, the lowest ground is the best. The graph is the best axis of the best. All right, so after solving this problem, then I have this simulation now. You can capture the non-knowledgeable factors and these equations are known. So let's response is going on to capture cell division that I showed you the picture of the data. It's going to capture cell division. Okay? And the first row is the usual way, the normal process. You have a single cell, it developing a little state, and then breaks it into 2, develop a little bit, then breaks it into 1. That's the normal process. And that's where alpha is 2. But alpha is 2 in my equation or in my model, you have to calculate. That's the constant. So okay, here are questions to write. This is one of the problems I have to explain it mathematically. When it's a single cell, I think on the row 1. When it's a single cell, T is 50 seconds, then 5,500 before it breaks into 2, right? 6,200 when it breaks into 4. When I reduce the alpha, the derivative order to 1.8, that's the second row. Look at the right one. Oh, good. So in this row here, in the first row, the first round is 50 seconds, right? When T is 3,000, it's already very basic. Remember that we took 5,500 seconds before the first one. Now at 3,000 is broken into 2. At 3,200 is already broken into 4. Right? You remember the slide I showed you before. When alpha is between 0 to 1 and 2, you have fast times 2. That's explained that it's faster. The process is faster. And then the last line, that's simple goes at T equal to 500, you already have process. So not only that, we capture the external and you can see these are the things that have been observed analytically. From cells break into 2 and 4. Some will just break for 1 and 4. Some will break into 2. And these are quality of very highly rated model. Because if we have the cancer cell that is well developed with just 6% dividing graphics. Next. And leading approval also means the application is parallel pattern, right? So in this case, you focus your attention, focus your view on equals, right? So in the first column there, that's when alpha is 2. You see the small square nature, right? So now I substitute alpha to be 1.8 into 81. We capture a lot of spiral nature. The last one is more multiple spiral. So this ability to see that, oh, I can see that after the fractional order in space is giving is capturing this definition that is over the because if this is second order, I will just get the question. What am I trying to do? Right? That's like it. So the case I showed before is called anticipativity. This one is anticipativity. Right? It just taking the orientation based on the constant value of that change. And the same thing is happening. You see, after is in the first here. 1.8, 1.6, you already see what's going next. Then changing the parameter gives you other level partners. And the same operation is next. Okay, so what I just showed you is integer fractional in space. That's what I just showed you. The question is, can I do fractional in time, integer in space, or fractional in time, fractional in space? It's getting more complicated, right? Now, let's forget fractional in space for now. Since we get into it already, let's focus on fractional in time. What would be the problem with that? Yes. So, when we do fractional in time, remember that when I represent a video that I showed earlier, I have matrix exponential, right? When you do fractional in time, what we'll get is not exponential. It's going to be what's called beta language. And that's thinking this way. E of alpha comma delta of t, which is infinite scale. And so this is D forward. The very good how do we approximate this so that we get to get something? And there is nothing you can do with time fractional derivative without the transfer distance. And so this is called generalized parameter without beta. If you get beta to be 1, that's you get compensate land, which is one parameter, just with argument. Is this function really important? Is it important? Oh, yeah. Very important. Let's see why it's important. Let's see. If you take alpha to the right in that function, compare that to the 1, you get the exponential function. It's exactly the Taylor series expansion of the exponential function. If you plug alpha beta to the 1, you change alpha to factorial, you get the Taylor series expansion of the exponential function. So exponential function is a special case. Not only that, other functions are also yes. If you can see minus 1 over t, it's also a special case. Yes. Cos square root of c is also a special case. Yes. Square root of b over c over square root of c is a special case. Yes. Cos z is a special case. Yes. 1 over 1 minus is a special case. So I just gave it 2 special cases. You can see how important this function is. So the question I've asked as a person is we found approximation to the exponential function. Can we find approximation, rational approximation to the numerical function as well? Not just that, the rational approximation function that can also within the properties of the moment time of the exponential function. Like being able to have three distinct moments. Two, being able to split the fraction into two. All right, so I'll come back to that later. Then let's look at this problem. Now, look at it very well. It's the same problem I gave you before. I remove fractional in the space, I put it in time. Now I change it to capital. Why? Because capital is the time of that item, usual not shared condition. How do you have one type of problem? Take your first problem. Okay, problem requires a space, right? You criticize the problem, the BD space, you get the system of ODU, which is the next one. Then apply your cost function. We don't have to push it down there. Yes. We are going to take the algebra, take the difference to our master, and then inspiration of constant formula. We get the integral. Oh my goodness, it looks exactly the same thing. We did not do it. The only difference here is that instead of exponential, we speak a little function. So that means so if I have a notation of exponential function, I can plug it into and freely what the optimal looking at a bit of can develop with efforts that, right? So next. So I then set out to develop rational representation function. This was done in 2017. And I did the analysis. We said acceptable, we asked for these people, and we set them to that. Very nice. The paper is website that you have to take it on. Next. Next. And so this is the way to choose the constant so that we can them. And then this is where I show that the cell acceptable. And I usually play this story when I come about this part. I gave up on this problem because I needed to show that it's well acceptable, and I didn't show it because I needed to have an inequality involving counterfunction, which I think will figure out. So I left this work for a while, and after that I was thinking about it. So one day I was looking at the paper, and we went to 1948. Very old paper, I write paper. And I looked, and I saw the inequality evidence. It was a game changer. I think this inequality which I gave last level of level, that God makes it easy at the first paper. Wow. I'm so responsible that paper and accomplishments. So, the good news about this representation that I just did is that if you take alpha to be 1, delta to be 1, what will get the mechanical function? The exponential function, right? So I was looking forward to see if I'm going to get the approximation we did for exponential function, where those parameters are 1 and 1. We did. Like alpha is 1 and delta is 1. You get the same rational approximation that we did for the exponential, which is extremely good, extremely important in case I'm going to make some comparison. Next. Just for a test of concept at this point, I plotted it against the error function. Error function is another function that is taken to come from mechanical function. So I plotted them together and you can see that the line comes. Next. So what is next? What are the input challenges? Next. This is so dense, no zero, right? People try to think, how do we get around this? What can we do? Because once you plug in a very dense interest, your completion is very slow. One method is to say, okay, you know what? I'm going to assume I don't have traction. I have just the classical case. I differentiate it, I get to try to outcome this. And I now put this matrix, and I put the estimate to be the fraction. That's from matrix transfer matrix. You transfer the matrix from the integer case to the non-integer case. Of course, I have done that one. You know. I showed the trade-off. We use something to play something, right? But it's very nice. If you don't care so much about using the error, but speeding up. So you are competing between speeding up and the error, right? Or if you are doing with data analysis, you are competing between speeding up and the error you get. So if you focus so much on speeding up, you will be increasing your error. So next. And the second point here is called short memory principle. Why do we have this method? If you look very carefully into the native G that I showed you for the person, it's not zero, but what we observe is that as we move away from the main diagonal to the right and to the left, the number becomes smaller. Very small. It's not zero, but it's becoming smaller, smaller, smaller. And so, for people to say, okay, if that is the case, let me turn off this at some point. It's not right for people like this. But I want to address those ones that they execute, they are fit. So they set a question to do that. Just turn that on, make that single, see if you can get a target on this fast thing. I didn't try that yet, but some work already done that, and it's able to be better. That is the theory. Then the third point is the called splitting method. This is A, right? Have the factors. We have the factors. Right? So the method of the problem, everything of matrices here, so currently I'm actually running constants on matrix theory and observation, which means the add is split add the factor matrix into pieces that can be easily added. Right? Like any factorization, p-power factorization, or less than a common. So that's the idea of split. You can split these things into 2 or 3 matrices that can handle each of them in a very simple way. Next. What can you see through with the existing method that was proposed? Remember, I use finite difference in time into space, right? To do the utilization. You could use other methods. One of my students was that we can use finite elements. We can use meshless method. We can use finite volume. We can try generalized. I think that is one thing that you can do. This is not the done. You can also extend your problem from reaction division, which what we call reaction division advection. Add an advection factor, which is more complicated, of course, but that is still purpose. And of course, developing time space skill, right? So in this one of the pages that is using the value bar which I just showed you to now construct a time space skill. Right. Also, the skill was developed to be a parallel. I have not tried the parallel, I can leave, I don't feel I've tried the parallel of integer things. We got tried it for some integer things. Next. Yes. Yeah, so we can consider several categories of to give the three things visit the university. Yeah, of course, when you have that question back, you need to have some complex problem coming up. What scale challenges is there? Yes. National level and national already. And there is something called domain decomposition. You can also decompose your domain so maybe you will able to solve the issues. Chief, and then you gather the down. And I think that's the end of my talk. And I only it's been a very intense interaction. If you have passionate question with it, if you want to like to write, never like to. No, not the kind of presentation when you want to say very good thank you. Now, I think that our guests have been standing for a very long time. We want to afford the opportunity of sitting to engage us, right? All right, please. Ushers, please come and help me here. We will just take this thing away from this place so that we can have our time to sit down. Yeah, we are scientists, right? When you listen to a very beautiful presentation like this, you don't just want to go that way. You want to engage using it. You want to engage using it. And I know there are people in the room who really want to engage. You know, Professor in deep thinking, in questions, clarifications, trying to see how we bring beauty of this talk out. And then we also have our online participants. It's time for question and answer. Now, for online participants, this is what we do. We want to engage people in the room first. So when we are done, we want you to signify, so with our media, we would help us take notes of people who want to signify, who wants to ask questions. Yeah, see, what we have done, now I'm saying to them. So they can raise their hand, just give the and just raise your hand. Then we come to you. Once we are done with the people here. Okay, so I don't know, we are going to be giving number. So you have to indicate if you have a question. If you have on the item who have question, there will be priority before we go on to the audience. Yes, and afterwards you can actually meet the our professor to ask question in case you want to your concern is not addressed. But like I said, it's time to engage in discussion. So I don't know, we have things on the item, so I will just give number on the item again. Okay, so Dr. Ben will take number 1. Okay, I'm not seeing any on the item, so Dr. Ben, step number 1. Now from the audience, you have questions from the audience, so you will take number 2. Are you raising your hand? You will take number 2. All right, Rosa Abola will take number 3. All right. All right, so you take number 4. All right, you take number 5. So in the room here, we have just 5 persons who want to ask questions. Number 6 is Samuel. And so number 7, Mr. Samson. Okay, so let's keep it at that. So if my questions are not asked before the hearing of this, I will also ask from the people online. I think just one person goes to my right. So we also ask questions. So over to you, sir.
Let me start with some existing protocols. I'm thank Professor Lee. I didn't know we met someone without others. I thank you for the lecture. When you were speaking, when we were looking at where to put your action at the visit, do you consider time or do you consider space? Then I remember when you study, then you mentioned something about slow diffusion and fast diffusion. And I remember slow, fast dynamics, like in dynamic system, when you consider a system that has that behavior, sometimes the behavior is slow, sometimes it is fast, maybe like in gene expression, or those kind of sometimes have a delayed. So I don't know if by maybe considering time in your fractionalization, whether one can begin to think of the slow scale dynamics, or how do it works, or let me put it the other way. If you consider only time, what do you want to achieve? Like when you analyze, you see if your method will give a faster approximation. Where did you place did you consider the coordinates or the time in your fractional derivative? Okay. Oh, just want to find unfortunately, combined right? You don't get back because what that means. Now we're coming from the application. Whatever application you are going to do with fairness in the not really beyond. All right. So that will tell you what you really want. For example, fractional in time handles situation that is memory dependent. So here is a problem with time fraction. If I'm looking for solution at T5, let's see. In classical case or integer order case, you just need the label of right? T n minus 1 and T something. Either for the case or for the case. We are dealing with four time fraction. If you are looking for the solution at T5, you need T0, T1, T2, T3, T4, T5. To find the solution at T5. So you need everything from that. So any application that has to do with memory dependence, meaning that you carry all these information from the past. For example, you are dealing with financial mathematics. If there is a price increase to do, that is not because of the right. Several things can related to the past. So that's another application. So when you are starting the application, that will give you what do you want to put into it, right? The space, I showed mostly with algebra system that I very want to show you. So in the slide that I showed, with different alphas, the alpha between 3 and which show the slow process. The alpha between 0 and 1 and 4 is space, which will processes. My problem, the one I showed, application is on space. Thank you.
All right, thank you so much, sir. We'll do it this way. I think the second person, so the ushers will help us pass the mic. So round so that we have those who have a mic then. Okay, so second person come forward then. Come forward. So maybe the third person should. The third person should move closer to that. You come forward. So when you want to ask a question, you tell us your name and where you are from. Is that okay? Good afternoon, brother. Thank you very much for the seminar.
My name is from Nigeria Maritime University, Warri. Sir, you mentioned about the application of fractional calculus to mechanics, most especially viscoelastic and viscoplastics. I want to ask if you have written any paper in that regard. You have talked about biological models. So have you ever written paper on it? And I'm thinking, can the fractional calculus, I think you have applications to solving structural problems. And my second question goes to the director. The sentence, international standards are applied with multiple value and that, but I'm seeing it as more of a biological models, modeling, and things. I'm not like, if you get a particular time in the future, where I think about this kind of conflict, that the biological models will be placed with the structural, then possibility of that, but it's
so Prof should respond at us.
I think the third concern is that I have not done applications with mechanisms, but in my thesis, I gave some very deep introduction to what has been done in that area. So there are so many natural integral that come from that area. That's just even one of those functional potentials. So natural uses. But it's really important. And there are so many work on that anyway. But if you look into my thesis, on Google Scholar, you can see my thesis as well. You will see a section where I discuss Abel's equation, viscoelasticity, and whatever. Yeah, so we are currently something in this next year that have to do with mathematical sciences, mathematics and application, general, not only to biology, but other aspects like clinical and all that. And we are really deeply with that specific area. So you work out. I've checked it. Thank you. All right. So your question is answered.
You are free, please come forward. Your name, where you are from, and then your question. Mr. Marbury, who? Good afternoon, everyone. I want to say, effectively, okay, my name, I'm Iyiola Olaniyi from the University of Lagos. Dr. Iyiola Olaniyi from the University of Lagos. In fact, I will say maybe I'm traveling away because of this beautiful talk I just listened to. That's why I forgot to mention my name. Sorry about that. So thank you to the speaker, in fact, Professor Iyiola. Thank you very much. It's an eye-opener what you have just presented. And I want to appreciate the organizers of this program, the Department of Mathematics, OE, and the Capital Center. Thank you for this. Yeah, my question is just one but in two parts. One of the beauty and why it should desirable, I mean, fractional calculus, especially when you have a fractional operator, it is because of the non-locality property and the ability to carry the memory effect. Okay. Now, in recent time, I see some guys developing some modification of this fractional calculus. One of them, they call it performable derivative. I don't know if you have heard of that. Okay. Which does not have, which is local. And it's able to carry factor the properties of classical derivative, which info capital does not even have. So my question now is, in this kind of application, Because like I just saw it, I tried to do some things to our own analysis anyway. I was trying to do some functional inequalities because we're able to do the derivatives to partial order. So and the thing carried just in a straightforward manner. And I'm now wondering, do we have this non-local property? Of course, no. Then what is the beauty of this? What it was just like it's just okay. So because we are able to do a lot of things that we not able to do with capital, we can do kind of like Lewis theorem, like a mean value theorem. You can, in fact, we even have this brief theorem which I apply in the case of fractional PD. So, but non-local. To my own understanding. So my question is, what is the beauty of it? If it works just like ordinary derivative, most of the results from classical, you can just carry them in a straightforward manner. So that is the part A of my question. Then second part, well, if that thing is, if the what I mean, the operator is good, can it be used for this your own case and it produce desired results?
Yes, so I know about component functional derivative, and many of them. There is an antagonal which I'm going to be using in GNSP. So, first, when you are dealing with fractional calculus, like I just explained, there is something behind your mind that you want this to capture, right? Conformable may not capture the local property nature, right? It's local, it's not non-local. That does not mean that there are no other features, right? That could be the interest of the person applying this, right? So it's a local operator, which means, and some people have tried to say, oh, don't call it fractional calculus or fractional derivative, call it conformable derivative. And so recently people have changed that English to, okay, let's just say it's conformable derivative. It's not the classical one. However, the goal of many recent definitions is to be sure that you can have the classical properties. Because everybody will like that. They can develop something that's not in line. Special case of this shape, what is so in each for that, you see something like that. And for me, I think it's more on the line of the application you want it. If you see that this application that I want need long locality, you cannot use that, right? For example, when I'm dealing with numerical central difference, I use global people. It's not useful for any other thing. And it's used for limit, which means it's local, right? So there are several situations where we use which are done, and it's inexhaustible. Yeah.
Thank you so much, sir. Number 4, please, number 1, very fast. Please let the people asking the question move closer so that when it gets to your turn, you quickly get to this place. Thank you. Thank you.
Good afternoon, sir. Thank you for the idea. So I have about 3 questions to ask you. So, this numerical solution, which of it have you applied in biological modeling out that you know and your experience? And the second question is, are there other factors to consider apart from time when it comes to application of numerical solution in cell division, section of your charts? And the last question is on matrix splitting. So I thought of something and I was like, can this matrix splitting of a thing be applied in DNA strand splitting as well? Like, those are my questions. So, I am just like our favorite script as we
Okay, I will try to remember. So the first one is about, is there, oh, okay, so the talk I gave, I showed the numerical development developed, right, which is called exponential time differencing with distinct That's what I used to solve this fractional models. And of course, I apply them to these Scott models and the visual model. But of course, I've done other applications. I did the work sometimes ago solving cancer model, where we are suggesting that the dynamics of so when you have a cancer model which incorporates killing rates. The problem is when the cancer when you have treatment, it goes away, right? And they say, okay, you are free, and then after some time it will come back. And so we need a model that can capture the coming back. And so when we did that work, we show that if you use classical integer paradigm, you can show that it goes away. If you use order, I think I suggested, I cannot remember the alpha value, which is not the integer base. We shows you the provider comes back. You can see the time effect too. So, yeah, I've done a couple of such applications too. The second one is about biological systems, which I showed in the application already. I am working on predicting breast cancer, if you regard as a biological system. We are also looking at incorporating human behavior into infectious disease model, like COVID-19. So I've done stuff like that. Matrix splitting. So the angle I've looked at matrix splitting before is mainly to reduce the computational costs, not from the application point of view. In that model, in that numerical scheme that I showed, there is a matrix A, and I'm finding a matrix exponential of that. If I can split this matrix into two, let's say using LGBT factorization, for example, where L is the lower triangle and U is the upper triangle, leading to that can be broken down and I can solve them cheaply individually. Right. That's what I am talking about when I'm talking about matrix splitting. Now, what you're talking about will be domain decomposition, right? Because it has to do with that specific application, right? So, which is also something that can be done, splitting the domain into pieces, which has to do with these matrices or let's say operators, and then using omega beta products to bring them back together.
All right, thank you. I really for your question. All right, repeat person, please come close. Your name, your school, and your person.
University of London. Thank you, sir, for this wonderful presentation. I would like to ask because when you are representing the work of various partners and programs, you know that with this integration to form countries and it's been tied with government in terms of countries. So I'm considering problems for how to give you an integer order of an integer used to solve problems and problems to the world. So, but my question is that though I'm still fully kind of against its solution, relevance, deep is the construction interface. Without a shift, can we employ certain analytical methods? Like this Adobe composition development is going to solve functional problems.
All right, sir.
Okay, so the question is, can we use several analytical methods to solve functional PDEs or ODEs? And the straight answer is yes. You can, and I have maybe 10 papers using the Google analysis method, Bayesian accretion method, Abelian methods, and that to solve modeling activities. So the challenge here is that you have to choose the kind of fractional derivative you are using. Because you can see in my presentation that the variability means integral time initial condition. And so you don't have that in some of these methods. So, but yes, you can use it.
Answer number 6. Yeah, let me first start by chasing the Prof. And also a counter to the very several degrees and the development of mathematics. So my name is Billy Nishikari from the Iyiola Olaniyi of mathematics and University Oye-Ekiti. So my question is to the response, the actual question to show us a problem. I'll upload that and just go to that slide as possible into. But I think all the things I saw there is a kind of initial value problem that you gave. So unlike the one I used to see, so this one was a kind of piecewise. So then I'm trying to think of so how did you really address that first? The way we're there, because of the time constraints, we've not even deeply into that. So I'm interested in maybe trying to dig deep into that as to how will you solve that, what people will do, what some different techniques and use to be used so that particular problem. And thank you, sir. So sorry, sir. Beside addition of the people that also recommend it, that will also give you understanding of that perfect. Thank you, sir.
So when you have a PDE and you have initial combination of various functions and others, the method that is using is not, so the initial conditions are not part of developing the method. So which means it doesn't matter what your initial condition is, we can develop a method to solve the PDE. What is problem from this one is that because there is something we call non-smooth initial condition. And so it creates some estimation. You see the function, the initial point is, let's say 0 point something %. 1% rate. There's a jump. So when we are solving that problem, remember we are taking some points. And so points here, we jump to the other one. So most methods we struggle to go up. Right. And so in order to test how good the method is, you are trying to solve this type of problem. Right. Not that the method is developed using the initial condition. I don't even need to know the initial condition when I'm developing the method. I just call it units. So that's let's see. That one. Oh yeah. So this work is published too. You will see in my previous scholar, if I don't remember the year, 2021. But this is the Scotland's, which you can published it. Once that my name, you can search some of the Scotland's.
So the seventh person, your name, where you are from, and your question. Good afternoon. So my name is Iyiola Olaniyi. I'm from the Department of Mathematics and also affiliated with Canada. So thank you so much for this insightful. So my question is, I work on my understanding that I'm relating the reflections to sometimes we use classical methods of American solutions. For a kind of nature like this, I want to see how I can maybe better something about America, because I think this aspect is more technical in terms of solutions and we use some of these classical methods, which is approximate solutions, and some of those approximate solutions will make inferences from there. So I'm looking at how what are some of the recommendations we have to better some of the American simulations. And the aspect of fractional, we made mention of some aspect of there are some intrinsic processes that happen maybe in the along the line of the American solution that most times you might not see it. So I just want to ask what are some of the recommendations you have around that.
So for the application into business model, right? I think it's dependent on the type of disease that you have disease in. I wrote I think it's 2 papers on COVID, for example. So, and what's the motivation? First, in Nigeria, the way COVID is spreading is different from how it's spreading in the US. It's different from how it's spreading in Ghana. So you come out, you do the first order in time, second order is first time, so we are modeling COVID everything. That's a problem, right? So we just do the simulation with fractional and time and fit in the solution to the new data and see that for this, the data from Nigeria, if you fit in the data to the solution we have, you need the derivative to be 1.8, 0.7, right? And then if you change that to another, you change it. So depending on the disease you are modeling and how it spreads, that will inform you of which the fraction, or even if you have to use fractional derivative at all, right? So, but if you go into mathematical scholar to get together about 2 or 3 papers, I did something on COVID, shatters,
Right, thank you so much. Before we go to our online participant, I also say my question and I was asked. So one of the things I want to ask, I want to first say thank you for the presentation. I think for you, one yesterday, Canada said it was a very good presentation. Say, deep into the network. Now, I'm looking at infectious diseases like they are said, I'm working on malaria and my PhD work. And most times, when you look at the dynamics of transmission of disease, for instance, you can just simply form with a certain ODEs, and then you are also able to bring in your data, fits the model, and it's able to give you what you want. But now, I'm not thinking about this. At what points would I know I'm supposed to use a fractional calculus for this problem when maybe if a flywheel is working perfectly, or maybe if it's not working, and I think maybe it's the order of the calculus that I'm using that's not good enough. At what point, what is the indicator for knowing what to use? Thank you.
I think that's a good question. If you are working in the particular application, for me, the red line is if what I'm getting is abnormal. If not the result of the past, what is going in the application you're trying to do is abnormal. For example, one person has a body, the following day, 1,000 baht body, and usual way of spreading that kind of disease should be maybe 1.5. This is something strange, right? From the and that's when I start to think about, oh, maybe I have to think of fractional other ODEs. I tell people it doesn't count. It does not count if you have fractional. When alpha is 1, for example, in 9, you have the classical. So whatever you get with the classical will still give you whatever you get when alpha is 1. When alpha is not 1, you will observe something that you can find out later that biologists or medical people have been struggling to explain why they are just observing that kind of thing, right? Like cancer spreading, right? Like tumor spreading in the body. There are so many situations where we cannot explain the spread. So there are several behaviors that we see and you cannot just explain why. It's like no. So that's where visual starts. Thank you.
Yeah, I'm sure Prof will want to say something.
Yeah, you challenge in vision scenario that you are seeing that like the point of view that the maths is the children. The question will become biology. So this kind of when we make use of mathematical tools, the direction is always like trying to see the maths and not what is basically going to be community in a unique situation. Now, I may put a particular control, maybe like control measure into a model, and then you are seeing that the thing is going down, or if you read that, it's not going down like that. You find out that the only thing is this spreading and all of that. So in most cases, I feel that, like all of these, actually every that we have talked about, fractional calculus, the OGP, normal classical OGP, the PDE, and all of that. I think the first thing you have to be, what is your question? So if your question has to be something that has to do with what fractional calculus can respond to, I think that's the question. So you don't just say, oh, I'm using calculus, and then you just go to open. No. The first point of view is that what do you want to happen? What's the motivation? What's the purpose? So because every model is also limited by the kind of assumptions or reason behind the model. There's no model that can actually answer all your problems. But we must be able to know that what is the question you have identified. Now, if you don't have a question, and then it means that you are not seeing anything, you need to go back and then address the question. Now, in addition to that, now we're talking about FDE, like fractional differential equation, the ODE, the PDE, the impulsive. There is even one impulsive that was doing the paper on that last week. Impulsive differential equation, and then what's it called? Multiple. So all of these stochastic is, has some uncertainties and all that. All of these are still deterministic.
Now, in the recent time, we have seen a lot of problems where you have to use certainties. So and that's where my question is coming now. If I have an FD equation, how do I bring in uncertainty into that system to be able to measure some uncertainty that I see, maybe in terms of the parameter or the state at the state level. So how do I induce uncertainty? Because from my own point of view, I think so most of the time like the other differential equation and then some PDE stuff. But for which we can develop into stochastic PDE or stochastic ordinary differential equation if I put some fluctuation into the model. So, but for FDE, and how do we address the aspect of uncertainty?
Okay, so before I say something on the question, first, the idea of fractional differential equation is not to say that the integer order differential equation is bad, right? And I'd like to clarify that in many places I've talked, because sometimes some people may think, oh, why would you say we should not use integer order and then use fractional? I tell them that's not what I'm saying. We've been using integer order case for, look at 1695 Leibniz Torvalds again. So none of this is pushing away the order. What we are saying, like I answered the first question was, and like you said, your application should tell you if you need to explore. And whatever you are doing, like the patterns that I showed, when alpha is integer, you should still get the results you should have gotten for integer case. So if that was bad in the first place, then part of what you are doing is bad as well. So one is not displacing the other. I can say that fractional is complementing the integer case, right? Now, coming to uncertainty, I haven't done any work into uncertainty PD or fractional PD, but I know a couple of people in Brown University, for example, who have incorporated uncertainty and do the analysis. What I do more is the numerical solutions now, not all the analysis. They're not the super simple.
So we will have to go to our online presenters. So please media, please let me know how many people's hands are up. I'm seeing H. Magao here. So once you unmute and then you speak to your mic so that we can all hear you. How many of them? Please, media, just 2 persons. Okay, so H. Magao, that's the name I'm seeing here. Please, can you go on and ask your question? Introduce yourself, your name, where you are from, and then your question. Thank you. Please unmute.
Hello? Hello? Can you hear me? Hello?
Yeah, we can hear you.
Yes, good afternoon, and sorry I came in late. I only got the link recently, but I just have maybe 2 questions. My name is Magao from the Central University of Technology in South Africa. Yes, the first question I would like to ask from the presenter, it's in terms of the interpretation of the different alphas that we'll have used, maybe just to get his view around that. And secondly, the second question, it's about non-dimensionalization. I had this question from Prof. McKinney at some point when I was presenting, and it has been battling in my mind for a long time now. That when you convert your problem to fractional order, that remember you introduced dt of alpha over dt alpha, right? So he was suggesting that we have to introduce a certain parameter that dimensionalize the whole problem so that we don't have an issue of dimension, because p to the power of alpha is its different meaning and a different dimension, sorry. Yeah, so maybe what's your input around that? That when you have a fraction, when you're converting an equation to a fractional order, how do you non-dimensionalize that system? Thank you.
One, the first question, you were talking about interpretation. The second question, you are talking about dimensionalization, right? But that second question is not so clear. I don't know if you can go over it again and then a bit slowly so that we can get you from this end. Thank you. Or if you can type, yeah, fine, that would be a good one. If you can type the second one so that.
So I can answer the first one. Yeah, so interpretation, I think it goes back to what we just discussed. If you are just so much curious, you just want to do fractional thing, interpretation may be a little bit difficult, right? First, you need to know details about the fractional calculus. What are the properties? What are the things you can gain from it? Now, the application you want to solve should give you idea about what you are expecting, right? So if you are like the one I did, I know that if I put fractional in space, I'm going to have super dilution, right? A process that is fast. So when I was doing my simulation, I was testing for different alphas to see if I capture that, right? So I am doing two things. It's showing me that the method I developed is good, right? It's not struggling when I have something like that. Two, that I am capturing the phenomena and I can see that the effect of putting the alpha in the first place is shown, right? So there's no one answer to, okay, how do I just interpret when I do this? You'll get something. If you don't know the application that you are using it for very well, it's almost impossible to interpret.
While we wait for Mandela to type his question, because we didn't hear that second part very well, I would like to read here. I have a question from Dr. Tico, and then some hands up that I will return to also. The question says, how do you employ the semi-group property in this area of research as mentioned during the talk? Secondly, for the solution described by the matrix exponential, what is the dimension of the matrix A, and what computational tool do you use to simplify or simulate to have estimates? Thank you.
Again, the dimension is not fixed, right? You have the domain, you split it into points. That gives you the dimension, right? So either you split it with the smaller subinterval, you have another dimension, or you split, or you have the domain, larger domain, the length of the, for example, the time. So
I think this person is talking about the dimension of the matrix, something like that.
Yeah, so okay. It comes from that when you equitize the point, right? It comes, the dimension of the matrix will come from the domain.
Employ semi-group property in this area of research, as you mentioned during the talk.
Okay, so theoretically, which I didn't show, we need to show the error estimate, right? So there are so many theoretical results that you need to use the semi-group properties to show. The good news, though, is that exponential function satisfy that property. So e to the a plus b is e to the a times e to the b. So we don't have, that's why I didn't go into that detail because I'm dealing with exponential matrix in this case. So that's it. With the Leffler function, the one I showed later doesn't satisfy that. That's one of the complexity that my student is working with. How do we get around that? Right? When the operator A is not just a matrix. So in general, when you want to prove some results, stability, existence, convergence, error, you need to assume that the matrix A is an operator. It's not just a matrix. And then you will need semi-group property.
Thank you so much. Okay, so we have another hand up. Julius.
Okay, yeah, good afternoon, everybody. Can you hear me?
Yeah, we can hear you.
Okay, so I want to say a very big thank you to my friend, Professor Bakari and Professor Iyiola. I am very happy for that very interesting lectures, and you can see that many students have asked questions. That showed that you have tried to, carry everybody along, and people are interested in trying to understand more things in this your talk. So I'll just go to my questions now. I know that there are several methods for finding the exponential of a matrix, for example, like the Kelp's method by Groutlet and Krylov's subspace method, Pade and Cauchy integral formulas. There are several approaches for finding the exponential of a matrix. I just want to find out if this your particular approach is similar to the Pade, but I just want to find out how easy it is for you to compute inverse of those matrices, considering the fact that for very important applications, the dimension of that matrix will be very large, as much as 10,000, for example, or maybe 100,000. So computing the inverses of those matrices, are they going to be very easy? That's one question. The second question is that I saw you use some Cranke-Colson, you use some BDF formulas. These are implicit schemes. So I'm wondering what approach you used in solving some of the nonlinear equations that may arise from these systems. After discretization and trying to solve with these implicit schemes, there are bound to be some nonlinear equations. So I want to know if you actually use some preconditionals, or maybe there are some other approaches you used to try to avoid some very high computational cost of this. And lastly, I find that your application in morphogenesis biological problem very, very interesting, where you have some kind of cell divisions. I want to ask, how were you able to have those? Because I think I want to know the actual what they call it function you used in getting those plots. Those plots where you have the cell division. Was it contour, or what did you actually use at the functions for getting those plots? Thank you very much.
Okay, so I'm trying to remember the first question. But let me start from the last question. So it depends on which one you want to get. So some of them I got using the contour, and some of them I using the solve plot in MATLAB. So these are just MATLAB call functions for plotting. And with the new MATLAB software, you can do a lot with plotting. I like using MATLAB a lot because it gives you beautiful plot and you can design it the way you want, using even LaTeX in it. So that's what we did there. In terms of
Sir, maybe you want to go over the first two questions briefly. Dr. Julius. Dr. Julius, it's like you're muted.
Oh, okay. So I can remember one of the questions talking about how do I deal with the inverse? Yes, so of course, when you deal with fractional in space or in time, you already have full matrices, right? The reason why we think our method is working better than the other method I compared with was that we were able to do the splitting, the partial fraction splitting. And once you do the partial fraction splitting, you have, I couldn't show the algebra, it takes about 3 pages, right? You can move things out, you can combine stuff, you can factor stuff, and at the end of the day, instead of having about 6 or 8 different terms where you have to compute the inverse, we just have 2 terms where you have to compute the inverse. So that's where we are saving the time. We still have to compute the inverse the way you compute the inverse, right? But in general, you reduce the times where you have to compute the inverse, and that's very helpful. And also, one of the questions is about how do I deal with the implicit stuff. So, what you do sometimes is that when you have an implicit method, you do what we call predictor-corrector thing. What happens is that you need to predict using a lower order method, which is explicit. Like Euler method is explicit, is first order. So I'm dealing with a second order method. So I use predict with Euler method, which is first order explicit. And that's the thing I use in the right side in the implicit case. So that's one way to go around avoiding fully implicit stuff.
Thank you.
Dr. Julius, I believe your question has been answered. Yeah, one person is asking if you can get slide. Yeah, are we going to get the slide? Okay, so yeah, it's with the media. As many of us who registered with us with your email address, it's been forwarded after the program. Okay, so we have a question here from the person who raised his hand earlier. Please, media, can you scroll up and let's see it? I can't see you have covered something. Okay, in a situation whereby the fractional, there is a question there. In a situation whereby the fractional DE has no exact solution, how do we know that the generated results via numerical methods are correct? 2, okay, yeah, I think you are at the second one that talks about, okay, but let me read it. What is the physical interpretation of the fractional order?
So, how do you know if what you are getting is correct, right? So, there's no exact solution. Here is the problem. If you are developing a numerical method, right, the first thing you need to do is to find a simple case with exact solution. And you may say, oh, is that, how do I find it? My advisor taught me this. You start with the solution. U of xt is t squared sine x. Differentiate with respect to time, differentiate with respect to space, plug them into your, and get the right hand side. And then you have an equation. Plug in 0 for t, you have the initial condition. So that's a simple way of generating a simple problem with exact solution to test your method. Now, when you run your method on that and everything is fine compared to the exact solution, then you have some rest of mind that if I'm applying it to an equation that does not have exact solution, then I have some level of confidence. That is one. 2, there are well-known methods like the one I compared with that are already shown to be very good, well established. So when you compare your results with those methods and it's doing well, that's another way to know that what you are doing is good, right? Thirdly, like I did, if I can capture some pattern or some phenomenon that is well known already,
then that shows I'm doing something right? So that is from the application point of view. And there are other ways. I know people solving engineering problem or some applications where they know how to compute specific features like energy. They know what the energy should be. They use the method to compute that energy, and then they compare that. So that's it.
All right, thank you so much. I want to give finally Dr. Olaniyi a chance to talk, and he said he has something to say.
Thank you for giving me the opportunity second time. Thank you. I will still appreciate our lecturer for today. He has done justice to all the questions raised. So I have a comment, and I don't just want to go away with that comment. I want to clarify to see whether I'm right or not. It is based on Dr. Dipo's question the other time when he was asking about the dimension of the matrix A. That is the equation you have there the other time. It seems to me as the semi-group form of the partial differential equation that you have. Okay, so that matrix A is usually called the generator of the semi-group, right? Okay, so if it is the generator of semi-group, it's supposed to be the dimension of the operator. In the case, if we are using Laplace now, if you have Laplace on a second, a space of dimension 2, and you diagonalize Laplacian, it's going to give you a 2 by 2 matrix. So in that case, that matrix is supposed to be of order 2, a 2 by 2. Of course, it's going to be symmetric as well. That operator A should be 2 by 2 and should be symmetric to see the positive definiteness of Laplacian. I think I'm correct, sir. So the comment I want to make is that A, the dimension should be the dimension of the operator that we are using. So I want to just clarify if I'm correct. That is my thought when you were teaching. Or maybe I say things, sir. That matrix A, okay, like that your equation now, that PD, you have Laplacian, the classical one. If you have that Laplacian, okay, that Laplacian is supposed to be of 2 dimensions with respect to x and y. So when you do that, you have a 2 by 2 matrix. So that A, matrix A that we have in that exponential TA, that is the generator of the semi-group operator, and the dimension is the dimension of the Laplacian operator that we have.
So it depends on what you are referring to in terms of dimension, right? What you say is correct, but that wasn't what I was thinking about the dimension, right? So what you are saying is when you have, we are talking of the dimension. Yeah, that's what you are referring to. But what I'm referring to is removing your mind from a 2D problem, right? Just fix your mind to 1D case. You have the spatial domain and you degretize it. That big matrix I showed, how big it is how many points you take. Now, the one you are talking about has to do with block matrices. Once you have more than one dimension, you have block matrices, right? So that's it.
So, in case you still have something to say to the presenter, it's going to be available after the program, so you can engage him afterwards. All right, thank you. Now we have essentially come to the end of this presentation and seminar for today. Can we clap for the presenter for that beautiful work done? Very rigorous, and that is how a scientific environment should look like. I'm happy also for Iyiola that has brought some of this kind of engagement for us to see what we are doing. And then to the undergraduates, I'm sure some of these things will still be looking like German, right? It's looking like they are speaking in an unknown tongue, right? Fine. That tells you that what you are doing currently, that you are not yet seeing the beauty. There is a higher dimension of it and the beauty of it. And you see people who are interacting easily with it. So, and you can become like that too. And I believe everyone seated here once saw mathematics like that masquerade that you are seeing it like that. But enjoy it now. It's okay. But build your interest as soon as you can see that it's even going into applications. And then over time, you will even be great at this by God's grace. Right? All right, so I give it to you. Thank you for staying to the end. Also bring the director of the International Center for Applied Mathematical Modeling again for this analytics to bring us a closing remark, as we draw the curtain for this today's event. You are welcome, sir. Professor Bakari. You are welcome.
Good afternoon. We started in the morning and now we are in the afternoon. Still standing on the existing protocol, I want to appreciate the Vice Chancellor in absentia, his representative, all the professors, the Faculty of Science, from Math Department, and my HOD. They have been here all through. Can you clap for them? Can you appreciate them? And I make clap for Math Department. We also want to thank our guest lecturer from Morgan State University. He left everything, coming down here from Lagos. He was in UI yesterday, gave a lecture at UI. After that, we picked him up at the airport. From there, we came to Akure. We couldn't get to because we left around 4, 5. So we couldn't continue the journey. We spent in Akure. Early this morning, we have to start coming around 6 or 6:30 thereabout, and then we are here. We want to appreciate you, sir, for giving it your time. It's not easy to put up after you have done everything. Put it up like this. It's not easy. It's not easy. So we want to appreciate you for giving time, proper time to give this a real deal. We want to appreciate you. We also want to appreciate every one of you for coming. We want to appreciate you for coming. Those of us that have come from Lagos, people came from Warri, from Buta, from many places. And I even heard, I'm so sorry, I've called them. People were coming from Osun State University, and they got to Aramoko, they had an accident, but I think they are being taken care of now. Somebody called me, like 2 people, they were coming for this meeting. I called them, and I think the situation is under control. So we really want to appreciate everyone for coming for this meeting, and we are praying that it's going to be an annual thing, that we engage in this kind of discussion, because or else the university is going to be done. We don't have this kind of activities going on, especially for math department. We want math department to be number 1 department in Oye. Yes. So we have started and we are going to continue. God will help us. We will bring people from Russia, from Kuwait, from Afghanistan, from India, from Somalia, and everywhere in the world. Thank you very much for coming. So before you go, we are going to take picture with the HOD and the guest lecturer and all the lecturers. It's going to be a memorable thing, So just get yourself set. Where can we have that? This place? Where are people going to start? Okay, So people are going to come, we will take picture.
Ushers, please come around.
Because some of you are going to be professors, years to come, doctors, directors, and then you see yourself that I was in that place, so look at that. You understand? So please do that. God bless you. Thank you very much. As soon as you finish, you have a lot of lunch behind you. You can pick your own and then enjoy yourself. Thank you. God bless you.
All right, thank you so much. Now, when we want to exit, we are going to honor our parents who are here Please listen. You can see that the people on the high table have been here since morning, and we want to give them the honor of exit. First, when it's to exit. So once they exit through this place, we lock this place because we don't want any influx to this place again. And then you can take your lunch at the back and then use the only one exit that we have in that place. Okay, so we want to take. Usher